Hi guys, welcome to Feynman Scholar. In today's video, we'll be going through electric field due to a dipole and specifically electric field along the axial line of a dipole. I hope you like this video. Subscribe to my YouTube channel, comment in the comment section and share my videos with others. Thank you. So let us begin. So let us understand what we are going to do today. So today we are going to find the electric field on a point which is kept near a dipole. This point can be kept on the axis of the dipole, or it can be kept on the equatorial line, or it is the perpendicular bisector of the dipole. So when we say that the point is on the axis of the electric dipole, that means in this line over here, it is on this line. So whenever it is kept over here, that point is kept over here, then we say that we are finding the electric field on this point, which is on the axial line of the dipole. When this point is kept over here, that is on the perpendicular bisector, or it is the equatorial line of that dipole that is going through the center of that dipole, then we are trying to find the electric field on that point which is kept on that equatorial line. So today we will be deriving an equation to find the electric field on a point which is kept on the axial line of that dipole. So first of all, let us take a dipole. We see this is a dipole over here. There is minus q charge and there is plus q charge over here. And we see that there is a point taken on this axial line, that is P over here. Now the distance between the dipole is 2a, and since it is 2a, that is from center to any of the charge, the distance will be a. Also in last video I told you that the direction of the dipole will be from positive to negative. That will be for physics, but I told that wrong. The direction of the dipole will be from negative to positive. This is for physics, and from positive to negative, that is for chemistry. So the direction will be from negative to positive. Okay, and this point P is distance x away from the center of this dipole. The center of this dipole is this point O. So from this point O to that P, the distance is x. So now we have to find the electric field on this point. So we see here that there is plus q charge over here, and there is a minus q charge over here. So if you want to find the electric field at this point P, what we have to do is we have to place a positive test charge. I have told this in my electric field lines video. What is a positive test charge? So we'll keep a positive test charge over here, and then on that test charge we will be finding the force. So we see that since here Q is much more near to this point P, therefore it will repel this test charge, which is positive, and this charge is also positive. That's why it will repel it in this direction, and this minus q point will, or the charge will attract it towards itself in this direction. Now we see that here this minus q charge, we have named it as charge 1, and plus q charge we have named it as charge 2. So here since plus charge is repelling it in this direction, therefore this one is electric field or due to 2, and this one is electric field due to 1. So we see here that this E2 vector, or this one, is much more bigger than this one. That is because this plus charge is near to this point P, therefore it will have more force compared to this minus q charge, which is way more away from this point P. Therefore we need to find the net electric field at that point P. Since we see that E2, it is much more bigger than this E1, the net force will be in the direction of E2. Therefore, that is, it will be in the direction of E2. This will be the E net, because E1 is way more smaller than E2. So therefore, this force will be subtracted from this force, and we'll get a net force, that is this one. So now we see that we are getting net electric field intensity, that is E2 minus E1. So we'll substitute the formula for electric field intensity. Electric field intensity is force upon charge. Charge is test charge over here, and then we get K capital Q by R square. This is the electric field intensity formula. So now we need to find the distance, that is the R square, or R we have to find. Therefore we see that from the center O, the point P is x distance away, and from the center O, the charge Q is a distance away, and the charge minus Q is a distance away. So the distance between plus Q charge and point P will be this total distance x and minus a. That is, it was not x distance away, it was a bit near to this point P, so we will subtract x minus a. So on this charge 2, that is plus Q charge, we get the distance is x minus a. Over here on the first charge, that is minus Q, we see that it is x from the center plus there is one more a over here, so we will add them, that is x plus a. So from charge 1 or minus Q, the distance is x plus a. So now we will substitute the electric field intensity formula in this one, that is E net is equal to E2 minus E1. So E net is equal to KQ by x minus a whole square. For the charge 2, the distance is x minus a. Therefore we substitute that x minus a value in R over here, and we see the magnitude of this charge Q is small q, so we substitute that also and subtract it from E1. E1 is k small q by x plus a whole square. So we get this. So from charge 1, the distance is x plus a, so we'll substitute that into R for E1. So we get E net is equal to k small q by x minus a whole square minus kq divided by x plus a whole square. Now we can simplify this equation. So first of all, we will take out this kq outside. From this, that is, we'll take common. Also, if you see over here, the charge, the magnitude of the charge for E1 charge is minus q, but the magnitude is only q. Here the minus sign gives the direction of the force. So we see here that kq is taken common, and what we are left with is 1 by x minus a whole square minus 1 by x plus a whole square. Again we can simplify this, so we will take LCM. So after taking LCM, we get this value over here and this value over here. We will take, so we will get kq x plus a whole square minus x minus a whole square divided by, we will multiply this two, we get x minus a the whole square, x plus a the whole square. Now this term we can simplify it over here. So this x minus a the whole square, x plus a the whole square, from this whole square we can take it outside, that is, we can take common for them, and after taking common we can see x minus a and x plus a. This formula we can write it as x square minus a square, and there is whole square outside, so x square minus a square the whole square we can do. So after that we can simplify this x plus a the whole square and x minus a the whole square equation also. So x plus a whole square we can write it as x square plus a square plus 2ax or 2xa minus this minus charge will stand inside, x square plus a square minus 2ax, but we will send this minus charge inside that, therefore it becomes minus x square minus a square plus 2xa or 2ax, both are same only. So from here we can cancel some values out. like here minus x square is there and plus x square is there, so we can cancel these two out. There is a square also and there is minus a square also, so this also we can cancel out. What we are left is plus 2ax and plus 2xa. So the final equation that we get is kq 4ax divided by x square minus a square the whole square. Now this we got for E net, that is this E net we can write it as E axial also. We can take E axial. So we can further simplify this by taking from this 4 we can take 2 here, 2 outside. This k will be here only. This q we can send inside. So we will get 2aq and then x. This 2aq, if you remember, this 2aq represents the dipole formula, that is P is equal to 2aq. This is the electric dipole. So we can substitute, instead of 2aq we can write it as 2kpx by x square minus a square the whole square. So this is the final formula, that is 2kpx by x square minus a square the whole square. But generally we see that x is much more greater than a, that is x might be in centimeters whereas a can be in micrometer or nanometer. Therefore if we take x square, so this, when x square will be there, then this a square will be much more smaller than this x square. This a square will be much more smaller than this x square. Therefore this a square, it tends to be 0. So therefore we can further simplify this equation by taking here a square over here. Over here we can see this a square, this whole term we can take as 0, and this square is there, it will multiply inside and we'll get kq 4ax divided by x to the power 4. So since x to the power 4 is there, so we can cancel this 4 and we can make it as cube, and then we can cancel this x also. So what we are left is kq 4a by x cube. So again we can get electric dipole from this, that is we will take from this 4 we will take 2, that is over here, then k will be as it is over here also, and then 2aq will be there. This 2aq again will become into p. So the final formula that we will get is 2kp by x cube. So this is the final formula for E axial, that is E axial is equal to 2kp by x cube. This is the final formula. Now there is one more formula for a point which is kept on the equatorial or perpendicular bisector of the dipole. This we will do in next video. So for today only this much. So now let us revise what we have learned. We have learned that electric field due to a dipole we have learned. We have seen that there can be two cases in this. That is when a point is on the axial line of the dipole, that is on this side. Then if the point is on the perpendicular bisector or equatorial line of that dipole. On the axis of dipole we have derived a formula. Over here what we did is we took a point P, which is distance x centimeter, meter, like that, away from that center of the dipole O. Now the distance between the dipole is A, so from center to any of the charge it will be AA. Then we got the net force on that point. This net force, we see that here plus Q charge is much more greater than the minus Q charge, that is the first charge. So we saw that our electric field intensity net will be E2 minus E1. So we substituted electric field intensity formula in this. Then we got the distance between them by, we saw here that from that point P to the center, that distance is x. So from on this plus q charge, that is our second charge, the distance will be x minus this distance a, and on the first charge or minus q charge, the distance will be x plus a. So we substitute the distance also in that, and then we simplify it. Then we got E axial is equal to 2k here, 2kpx by x square minus a square the whole square. But we saw that generally x is much more greater than a, because x might be given in centimeters like that, whereas a will be given in micrometers or nanometers. Therefore when we squared this x square and a square, this x square is much more greater than a square. Therefore this a square, it tends to be 0. So we neglect that a square term, and then we get x to the power 4. This x to the power 4 we can again cancel from this x which is present over here, we can cancel it, and then we can get k cube 4a by x cube. Again we can write this in terms of electric field, uh, electric dipole, and then we see that E axial is equal to 2kp by x cube. Here we can substitute the value of k also. The value of k we can write it as 1 by 4 pi epsilon naught. So thank you guys for today, this much only. I hope you like the video. Subscribe to my YouTube channel, like my video, share it with others. Thank you.